Okay, now we will discuss about combinatorial optimization problem. Right, so why we are discussing about the combinatorial optimization? Because most of manufacturing system problem are involving the combinatorial optimization. Okay, so some definition of combinatorial problem. It is involve finding the best arrangement, selection, or combination of element from a finite set of option. So we have a set of option that we need to identify the best combination, the best arrangement, or the best sequence. So this is about the combinatorial optimization problem. Okay, so there are a lot of application in manufacturing system, okay, such as production scheduling, assembly line balancing, assembly sequence planning, aggregate planning, and so on. So there are a lot of application for the combinatorial problem. And the combinatorial problem is a discrete object, and this problem deal with the discrete entities or object. Okay, so we are dealing with discrete object or discrete parameters. So the objective of this problem normally to optimize the objective function that we set or satisfy specific constraint. Okay, so we need to set the objective function for the problem, and later on we will work out how to calculate the objective function and then code them into related programming tools, and then finally optimize the objective function that we have coded. Okay, one of the popular example in combinatorial problem is known as traveling salesman problem. Okay, so this is a problem that has been researched and also has been implemented in a lot of application. So basically, for traveling salesman problem, a salesman need to visit a number of finite cities, okay, in the most fastest way. It may be in terms of the fastest time or the cheapest cost, and so on. Okay, so finding the shortest route, okay, that visit each city once and return to the starting point. So when we have a lot of point or a lot of cities to be visited, so of course we need to plan our route. Okay, the route must be the traveling distance must be the shortest, or maybe the traveling distance should be the cheapest, and so on. So we need to identify the best route in order for us to visit the cities. Then another example is knapsack problem. Okay, selecting a subset of item with maximum value while respecting a weight constraint. Okay, so this is one of the popular problem in combinatorial, where we have a limited carrying capacity, and we want to take as much as item that we have, but of course we would like to select the item which has the highest value. Okay, for example, if we combine this item in green color 12 kg with this item 2 kg, so the value is only $6. Okay, but if we take this item 4 kg combined with other items such as in blue color or in a gray color, okay, so the value is already $14. So this is one of the example of the problem where we have a limited capacity of carrying, but we need to choose which item that we need to collect. Okay, in real world application, the application might be in term of production scheduling. Okay, for example, if we have 10 jobs and we have a limited time, okay, it must be maybe the given time frame is only maybe 10 hours. So of course, if we look at the time required to process all the 10 job, the allocated 10 hours is not enough. So we must choose a proper job to be performed within the given time frame. So this is one of the application for knapsack problem. Then job scheduling problem. Okay, so sorry, job scheduling problem, which is assigning tasks to machine or workers with objective of minimizing the max span or total completion time. Okay, so this is another example. Okay, so for scheduling problem, we have a set of job to be processed and we want to minimize the total completion time for all the jobs. But in it's slightly different with knapsack problem. For knapsack problem, we also have a set of job, but we have limitation in terms of the processing time. So maybe not all of the job can be processed within the allocated time. So we need to choose which job to be processed within the allocated time. So this is for knapsack problem. But for job scheduling problem, uh, we want to process all the job and we try to minimize the total completion time. The total completion time is not being set as what we call as a constraint. So we have freedom to complete the job within uh, we have what we have a freedom to complete the job, but we are prefer the solution that come out with minimum processing time, okay, or minimum total completion time. Okay, so this is the job scheduling problem. And as I mentioned, for combinatorial optimization, there are lots of application. Okay, in operation research, logistic and supply chain management, network design and routing, okay, resource allocation, VLSI design, even in the cryptography. Okay, so there are a lot of application that involving arrangement of the sequence or arrangement of the job arrangement of the allocation that we have. So in the end, we will get the best solution that fulfill our optimization objective. But the key challenge for a combinatorial problem is the large solution space. Okay, the number of possible combination can be exponentially large, making exhaustive search impractical. Okay, so now we are dealing with the possible combination. So the possible combination of the job, of the task and so on can be exponentially increased. Okay, for example, if we have maybe let's say five job or five tasks, so the possible number of combination is can be calculated by 5 factorial, which is only 120 possible combination. Okay, but if we increase the number of job or number of tasks, number of item to 10, for example, if we have 10 job or 10 tasks to be completed, so the number of possible combination for this one is more than 3 million. Okay, so uh, by utilizing the exact method, so it's quite impossible to solve this problem within acceptable time range. Then number two is the algorithmic efficiency. So finding an optimal or near optimal solution efficiently is a key challenge. So for the combinatorial optimization problem, the efficiency of the algorithm is very crucial, very important. Okay. As you know, for metaheuristics algorithm, we didn't promise or guarantee the global or the real optimum solution, but the near optimum solution is already good enough for the combinatorial optimization problem. And problem specific constraint, each combinatorial problem may have its unique constraint and characteristic that need to be considered. So of course, each of the problem have their own constraint. Okay, maybe in terms of the logistic and supply chain management for the vehicle routing. So maybe it has a certain time frame or time window whereby the collection and also delivery must be conducted within a certain time. In production line or the assembly line balancing, maybe the most crucial constraint is the sequence or the precedence of the assembly process. So we cannot conduct the assembly that have the precedence constraint, okay, before the precedence process is being completed. So these are some of the constraint that we need to consider in a combinatorial optimization problem. Then designing problem representation for combinatorial problem. Okay, so for problem representation, the way we represent the problem affect the efficiency and effectiveness of solution algorithm. Okay, so as I mentioned in earlier video, the problem representation play a significant role in the efficiency or the quality of the solution that we obtain. Okay, so again, for combinatorial optimization problem, which involve arranging the task, sequencing the job, and so on. So it is not it's not possible for us to directly use the standard continuous representation for the problem. Okay, so one of the key consideration is several factors should be considered while designing the problem representation. So we need to consider a lot of factors before we finalize the problem representation to be used in our problem. Okay, maybe for the combinatorial problem, the problem representation for one problem will be different with this with other problem. Okay, all right. So some factors to be considered, okay, during the uh, problem representation design. Okay, fact the first one is the decision variable. So identify the essential decision variable that capture the problem's key element and characteristics. Okay, decision variable that we need to utilize in order to optimize our problem. So we identify the essential decision variable, okay, or the crucial decision variable that directly influence our output indicator. Then encoding, choose an appropriate encoding scheme to represent the decision variable in a compact and meaningful way. So we try to design the encoding by as simple as possible, but it can represent the problem that we are dealing with. Then constraint, ensure the problem representation can handle and enforce the problem specific constraint effectively. And the solution space, define the boundaries and structure of the solution space to guide the search for optimal solution. So these are some of the factors that we need to consider when we designing the problem representation, okay, for combinatorial problem. Okay, again, decision variable. So what are the decision variable that we are utilizing? Is it the sequence of the operation, the allocation of a certain resources to a problem, and so on? So we need to define this one. Then encoding. So encoding is the way we encode the problem so that it will have a proper integration with the standard algorithm, And at the same time, we also define the decoding, which will transform back the continuous representation that we use into the meaningful problem, or meaningful value for our problem, our combinatorial problem. Then constraint. Okay, so we must consider the constraint that involved with the problem and the solution space. Okay, for example, for TSP problem or traveling salesman problem, so the decision variable are the sequence of the city or permutation representing the order of we visit the city. Okay, so city sequence. So this is the decision variable. So when the sequence is changed, our route distance or our objective function will also change. Then encoding. Okay, so we encode using permutation based encoding. Okay, using integer or binary strings. Okay. Then constraint, ensure all city is visited exactly once. So we cannot visit the same city more than once, and the sequence start and end at the same time. At the same city. So this is the constraint that we need to consider. Then solution space, enumerate all possible permutation or use heuristics to limit the search space. Okay, for the search space, so one of the possibility is to generate all possible permutation, or we limit the search space by using a certain heuristics. As an example, for traveling salesman problem, okay, let's say we have a simple traveling salesman problem consists of 4 points or 4 cities to be visited. Okay, so the optimization objective for this example is to minimize total traveling distance. Okay, to minimize the total traveling distance. So the decision variable has been set earlier. So the city sequence or permutation that representing the order of visit. Okay, for example, sequence 1, the routing will be from 1, 4 to 3. Okay, 1 going to 4, 2 and 3 and return back to original position. Then sequence 2, 2, 3, 4, 1. Okay, starting from 2, 3, 4 and 1, and then return back to original position, which is point number 2. So if we assess these two sequence, so we will get the different result in terms of the total traveling distance. Okay, so this is the example of optimization objective and also decision variables. Okay, so in this case now, the decision variable is the sequence in the form of permutation. Okay, so if we refresh back on the spring example that we discussed in earlier video, so we have the combination of continuous variable as well as the discrete variable. But in this example, we have the permutation variable. So how to represent the city sequence in our model? So we can use the permutation between 1 and n. So n is the total number of cities. Okay, so as being set or as been shown earlier. So this is just two examples. So we can create more sequence of traveling. Okay, so the algorithm or meta-heuristic used must be capable to handle permutation representation. Okay, so as I show in the earlier video in PSO example, that one is utilizing the continuous representation. Okay, so we need to design an algorithm based on permutation. Okay, so most of the standard algorithm are developed based on continuous representation, but our problem in combinatorial are mostly based on the permutation. Okay, so if we recap back the PSO example, okay, in initialize stage, so when we create a random solution, so a value of variable 1 and variable 2, all of these variables are the continuous representation. Okay, all of these variable value are the continuous data, continuous representation. Then for represent TSP, okay, representation for TSP, if we utilize the standard PSO approach in initialized stage, so the representation must be using the permutation. Okay, this is the permutation base between 1 to n. Okay, so this is example of permutation. And if we look back at the PSO operation at the reproduction stage, okay, which is update velocity, okay, and the calculation, related calculation here, omega, C1, R1, P base, and so on. So all of this value or all of this calculation are using the standard arithmetic, which involve the continuous number. Okay, so when we are coming to update velocity and position, so it involves continuous calculation. Okay, so when we are using the permutation representation, we cannot utilize this mechanism or this calculation to update our particle, update our sequence. So it will not work. So if we still utilize this one, finally for the new population, it will come out with the continuous number. So means that it already not representing our TSP problem. So that a new algorithm is required to conduct arithmetic for permutation representation. Okay, so in order to conduct the calculation for our permutation representation, so we need a new algorithm. Okay, so means that this is what we call a quite large job need to be conducted in order to fit our problem representation to the existing optimization algorithm. Okay. So as I mentioned earlier, majority of standard metaheuristics, okay, and code developed using continuous representation. So how to deal instead of designing new algorithms. So as I mentioned, to design a new algorithm is quite a big job. Okay, so what option do we have instead of designing new algorithm? So we can design an encoding and decoding scheme, okay, in order to fit, okay, our permutation problem into the continuous representation in standard algorithm. So encoding is a represent the problem variable in a suitable format for optimization algorithm. So representation of the problem variable in suitable format for optimization algorithm. So means that if we are utilizing the algorithm that developed based on continuous representation, so we also must use continuous representation to represent our problem. Okay. So again, in our example, we are using the permutation representation for TSP, okay, but our standard algorithm, as I showed earlier in PSO, are using the continuous representation. So we need to have encoding and decoding scheme. Okay, again, encoding is a representation the problem variable in suitable format for optimization algorithm, and decoding is transform the encoded representation into meaningful value or configuration. Okay, decoding is transform the encoded representation. So when we encode, let's say in continuous space, so we need to transform them into meaningful value for our TSP problem. Right? All right. So now, when we have encoding and decoding, so we have originally our TSP problem, okay, is represented using the permutation. Okay, but the standard algorithm is in continuous representation. So this is example of continuous representation. This is example of permutation representation. Okay, So we need to encode the problem. Okay, encode the TSP problem into a continuous representation. And then when we encode into continuous, we must decode it back, okay, into the meaningful value for our problem. Okay, for if we look at this example 0.24, 2.5, we cannot relate this value for the TSP problem, because for the TSP, as we discussed earlier, the decision variable is the sequence of cities to be visited. So if we just look at this number 0.24, 2.51, 9.2, and so on, so we cannot directly relate this value to represent the cities to be visited in the TSP problem. So that's why we need to have a decoding scheme in order to convert this continuous representation into a meaningful value to represent our TSP. Okay, so now 2143 is considered as meaningful value because this value can represent the sequence of city to be visited. Okay. All right. So for encoding scheme, okay. For example, here TSP problem with n equal to 4. So we create n random number between 0 and 10. Okay, so now we want to encode our TSP problem into continuous representation. Okay, so now we encode our TSP problem into continuous representation. So we need to create n random number, okay, between 0 and 10. Okay, basically this is based on our setting. It might be between 0 to 1, it might be between 0 to 100, maybe between 1 to 100, depend on us. Okay, so for example, x1, so this is the continuous number for to represent the problem. Okay, so this is the encoding that we use in our problem. So now this value can be directly be used in a standard metaheuristic algorithm such as in PSO that we have discussed earlier. Okay, but how this number can be used or can be transformed to represent our traveling salesman problem. So that is the issue. All right. So this is continuous encoding that compatible with standard algorithm code. Okay, so decoding scheme. So now we want to transform our representation here, or this one, into the traveling salesman problem variables. So how to transform them? So one of the approach that we can use is to assume our x1 until x3 as a factor or weight for the TSP cities. So for the cities, we have 4, point 1 until 4, and we will assume x1 here is the factor or the weight for the TSP cities. Okay, so what we can do is we need to set a rule. For example, we need to set the x value in ascending order. Okay, the x value here can be defined as the weight, and we sort our cities based on the weight here. Okay, if we sort in ascending order, so for x1, the TSP sequence will be like this. Okay, so for x1, if you look at the value here, if we sort in ascending order, so the smallest value will be 0.1. So this one is representing city number 2. So city number 2 will be visited first. And then after 0.1, the next value in ascending order is 1.94, representing city number 4. Okay, so city number 4 will be in the second order. The next is 4.67, representing city number 3. So city number 3 will be visited in the third order. And finally, city number 1, okay, 6.12. Okay, so from the continuous representation here, Okay, if we use this rule, so we already can decode the continuous representation into TSP sequence in order to visit the cities. Okay, 2431. So again, this one is coming from the sorting of this value in this in ascending order. Okay, for x2, the smallest value is 3. So the city number 3 will be visited first, then city number 2, okay, then city number 1, and finally city number 4. Okay, so this is one of the option that we can use. Let's say you want to sort, you want to use the rule where you need to sort in descending order. So for x1, you need to start with the largest x value, which is 6.12. So we will start from city number 1, then going to city number 3, city number 4, and city number 2. And of course, finally, you need to return back to original position. Okay, so this is one of the option. So once you already obtain the sequence, okay, the sequence in the permutation order, the sequence to visit the cities in the permutation order, so you can calculate the distance. Okay, 2 to 4, so from 2 to 4 is 12, plus 3 to 4, 3 to 4, sorry, 2 to 4, okay, 12, then 4 to 3, 4 to 3, 18, so 12 plus 18, 3 to 1, 3 to 1 plus 18, then finally 1 return back to 2, okay, 10. So suppose the distance is 58. Then for x2, so if we evaluate the sequence for s2, so the total distance will be 54. For x3, sequence 3, this is d3 equal to 56. Okay, so from here basically we can calculate our fitness function for this problem representation. Okay, so basically from this example, suppose you can capture that we are represents our problem in continuous space. Okay, after that we decode the continuous representation here into permutation as we define in TSP, and then after that we calculate our objective function based on the decoded solution. Okay, and then we can define the fitness for each of the solution or the continuous representation here. Okay, this is the general PSO example. Okay, this is the standard PSO example. Okay, so just the same diagram as in the earlier video. So initialization, fitness function, fitness value, update P-best, G-best, update position and velocity, and so on. So basically for standard PSO, all of these value are in the continuous order. But when we want to implement the combinatorial problem or the permutation representation for our standard PSO, so the flow of PSO will slightly being modified, okay, like this. So from initialization of the particle swarm, so when we create the initial solution, so we need to decode the problem into the TSP representation first, and then it will be evaluated. Okay, the fitness function will be calculated. Then we follow the update P-best and G-best as usual, and so on until the termination. So if the termination criteria is not satisfied, so it will go back to the decoding. So remember, for the PSO algorithm, after update position and velocity, it will create a new solution. Okay, the new solution will be decoded back, and then the new solution will be evaluated. Okay, and all the representation for PSO is still remain under or using continuous representation, but for the decoding, so this one will be utilizing the permutation representation for TSP problem. Okay, so as a summary, so encoding and decoding scheme help to utilize standard metaheuristics algorithm code. So it is not necessary for us to develop the whole algorithm to suit with the combinatorial problem. So we just need to make a small changes here on the decoding, and then we can fit our approach or our problem to the standard PSO or standard metaheuristics algorithm. So the key in order for us to implement any kind of optimization problem using the existing algorithm is the decoding scheme. Okay, so we need to design a proper decoding scheme for the problem to transform the continuous representation into the representation that really represent our problem. Okay, so that is the normally the task for any researcher, okay, to develop the decoding scheme that represent their problem so that they can utilize the existing optimization algorithm for their problem, even though their problem is not really in the continuous space.